Hi, my name is Andrian. I'm a software engineer. Today, I'll show you how to build an interactive 3D website using React and Three.js. We'll start with a 3D watch model and create a series of scroll-driven animations, as well as explore how to dynamically change materials and textures in the scene based on user interactions and application state. This won't be a superficial tutorial. We'll begin with the fundamentals of 3D graphics, breaking down how 3D models are structured, exploring different types of materials, and understanding how lighting affects the final visual result. Next, we'll look at the tools and workflows used to create and prepare 3D models for the web, ensuring they are optimized and production-ready. Finally, we'll explore several approaches to building animations and visual effects that make the interface engaging and enjoyable for the user. Before moving on to development, let's define the set of tools and technologies we'll be using during the implementation. We'll need a watch model, which can be downloaded for free from the internet. However, before using it, the model must be properly prepared. And for that, we'll use Blender, a professional tool for working with 3D graphics. We'll also be dynamically changing object textures. To create them, we'll use Canva, as it allows us to achieve fast and practical results. You can use Canva as well, or any other image editing tool you prefer. The interface of our project will be built with React, a modern library for creating dynamic, component-based user interfaces. For working with 3D graphics in the browser, we'll use Three.js, one of the most popular tools for building real-time 3D scenes on the web. To seamlessly combine React and Three.js into a single, cohesive system, we'll use React 3 Fiber. This library allows us to write 3D logic declaratively, using React components, while fully synchronizing rendering between the UI and the 3D scene. To manage global state and application logic, we'll use MobX, and for certain animations and transitions, we'll rely on GSAP. Let's take a closer look at the functionality we need to implement. When the application starts, smooth animations appear on the screen. As the user scrolls, the watch model begins to change its position, transitioning into the next section. Next, the model stops, but its internal elements continue to animate. When hovering over an element, the model changes its material. On this screen, we can also adjust the camera angle. Continuing to scroll leads to the next section, where the user can select a color. When a color is selected, both the model's material and the overall theme are updated. On the final screen, the previous elements move out of view, a button appears, and animated screens slide in from the sides. The color of these screens depends on the currently selected theme. I'll start by creating a React project using Vite and selecting the TypeScript template. Next, I'll install the required dependencies and clean up the default project files. This is how the website looks at the moment. I'll then define the base styles by removing default margins and setting a black background color. After that, I'll install the libraries needed to work with 3D graphics. However, before using them, I'll first go over the basics. When we work in a 2D space, such as an HTML document, we deal with two axes, X and Y. To define the size of an element, we use properties like width and height, along with different measurement units. To change an element's color, we work with the background property. In 3D graphics, objects consist of geometry and material. Geometry defines the shape of the object, while the material defines how it should look. Together, they form what is called a mesh. There are three main types of transformations we can apply to a mesh: position, rotation, and scale. In an HTML document, we can change the visible area of the screen relative to the document by scrolling. In most cases, scrolling happens along the y-axis. In 3D, to display a specific part of the scene, we use a camera. The camera can be moved or rotated, and everything that falls within its view is rendered on the screen. So if we compare these two approaches, the workflows are quite similar. We can create elements, define their size, and position them in space. However, in 3D, an additional axis is introduced, along with a camera and lighting. Objects are also split into geometry and materials, which together define how they are rendered. In the earliest 3D engines, geometry consisted of vertices and edges. A vertex is a point in space, and its position is defined by 3 coordinates. If you connect 2 points, you get an edge. By combining multiple edges, you can create a cube, a sphere, or even a car. In general, there are no real limitations. However, without filling the inside, such models look incomplete. That's why faces were introduced later. A face consists of 3 vertices, and it can be filled with a color or a texture. When working with interactive engines like Three.js, you usually don't define vertex or edge positions manually. Instead, you are provided with a basic set of primitive shapes, such as a plane, cube, circle, sphere, and others. In most cases, you can also specify how many segments or edges are used to generate the shape. In contrast, in 3D editors, you can work directly with individual vertices, edges, and faces, allowing you to create highly realistic models. A surface is defined not only by its color or texture. There are 3 main parameters that determine how a surface looks in modern graphics. Roughness defines how matte or smooth a surface is. A value of 0 represents a perfectly smooth surface, while 1 represents a fully matte surface. Metalness. 0 represents non-metal materials such as plastic, leather, or wood. 1 represents metals like aluminum, steel, or gold. Emissive defines how strongly an object emits light. The combination of these values is called a material. The 3 parameters we discussed are part of the standard material, which also defines additional properties internally. There is also a basic material, which contains almost no physical properties, only color, texture, and a few extra settings. It does not react to lighting, which is why it's often used for UI elements or icons. In addition, there is a physical material, which includes everything the standard material has, plus extra parameters that make it as realistic as possible. And finally, if none of these options fit your needs, you can create your own custom material, known as a shader. The basic material does not react to lighting, so even if there are no light sources in the scene, the geometry will still be visible, unlike the standard and physical materials. There are 5 main types of lights. Ambient light emits light evenly from all directions and has no specific direction. It does not cast shadows and is mainly used as fill light. Directional light works like the sun. It has a direction and emits parallel rays. It can cast shadows. Spotlight emits light in a cone shape, similar to a spotlight. It's commonly used for accents or focused lighting. Area light appears as a rectangular light source in space. Point light works like a light bulb, emitting light equally in all directions. In the root component, I start by adding the canvas element. This canvas acts as a wrapper for the entire 3D scene. All 3D objects will be rendered inside this container. I apply styles to make the canvas fill the entire viewport and keep it fixed on the screen. After refreshing the page, we see an empty screen. That's expected. At this point, nothing has been added to the scene yet. Inside the canvas, I place a mesh. Within that mesh, I define a box geometry and apply a basic material. In React 3 Fiber, we can declare 3D elements using JSX syntax. Under the hood, this JSX is converted into Three.js objects and function calls, which then send commands directly to the GPU to render the graphics. As you can see, JSX makes defining 3D elements much easier and more convenient. The trade-off is that React adds an extra abstraction layer, which may introduce a small performance overhead. For highly complex or performance-critical scenes, Using pure Three.js is often a more appropriate choice. Now I can experiment with the mesh, change its position, rotate it, or move it around in space. I can also adjust the camera, move it back, change its initial position, or modify the field of view. Next, I enable orbit controls. By default, this allows me to rotate the camera around the center of the scene. The rotation radius is determined by the farthest distance from the center. I add another cube to the scene, but this time I use a standard material, one that reacts to light. At this point, the geometry disappears. This happens because there is no light source in the scene. I can fix this by adding ambient light, and I can also introduce a directional light that behaves like the sun. When I move the directional light, the lighting angle changes accordingly, affecting how the object is shaded. In this video, I'll be using a free watch model. You can download a model from any platform you prefer. If possible, I recommend choosing models in the GLTF format. It's a modern format optimized for fast transmission and rendering in the browser. In many cases, all the required data is stored in a single file, which makes importing the model into a 3D editor or engine very straightforward. I found a free model like this, and I'll leave the download link in the description. To work with the model, we'll need a 3D editor. I'll be using Blender. It's completely free and widely used in professional workflows. When you open Blender for the first time, the amount of settings and features might feel overwhelming. But in this video, we'll focus only on a few essential tools. Once you clearly understand what needs to be done, the workflow becomes much simpler. Let's briefly go through the main tools and panels we'll be using. In the top right corner, you can see the list of objects present in the scene. In our case, it's a cube, a light source, and a camera. The cube behaves exactly like the one we created earlier in Three.js. I can move it, rotate it, or scale it. In the top left corner, there are several interaction modes. We'll mainly be using the first two. Object mode is used for working with entire objects. Edit mode allows us to work inside an object. In edit mode, I can manipulate vertices, edges, and faces. Blender also provides multiple viewport shading modes. I can switch between wireframe view, solid view, material preview, and fully lit mode. Materials are configured in a dedicated tab. When I switch to this panel, I can see all the materials assigned to the mesh and modify them. For example, I can change the base color or adjust the metallic and roughness values we discussed earlier. What's even more interesting is connecting textures to the geometry. Instead of using a flat color, I can apply a texture and choose an image to add more visual detail. Now I'll import the model we downloaded earlier. In the top left corner, under the File menu, I select Import and choose the appropriate format. The downloaded file may contain a lot of unnecessary elements, as is the case here. We'll need to manually remove everything we don't need. It's important to understand that in this video, I won't cover every detail of 3D modeling. Otherwise, this lesson would become far too long. Instead, I'll walk you through the full production pipeline, provide a ready-to-use model, and if you later improve your modeling skills, you'll be able to create your own assets. After cleaning up the scene, only a few meshes remain. I'll move them into a separate collection to make the workflow more organized. Next, I need to split the model into multiple meshes, 10 in total. These include case, strap, display, antenna, crown, sensors, battery, microchip, vibration motor, and speakers. Some of these elements are already separated, while others require additional work. For example, the antenna is currently merged with the case. I can detach it into a separate mesh and rename it accordingly. Next, I'll pull out the internal components, similar to what we saw on the second reference image, to make the structure easier to understand. The display is also attached to the case. To separate it, I can switch to the Material tab, select all faces that use the display material, and then detach them into a new mesh. Any remaining unnecessary geometry should be deleted. The inner part of the speaker is inside the model, and I'd also like to merge it with the outer part. It's worth mentioning that the model we downloaded doesn't have perfect topology, and there are some visible artifacts. However, these parts won't be visible to the user, and finding high-quality free models is not always easy. A better optimized model is always a plus, but since our time is limited, we'll continue working with this one. Another important concept I want to demonstrate is face direction, or normals. If I enable the corresponding view mode, I can see which direction each face is pointing. While 3D editors often render both sides of a face, real-time engines can have issues with this. I can change the face direction using specific tools and shortcuts. To demonstrate the problem, I'll create two cubes and flip the normals inward on one of them. At first glance, they look identical. But now let's try importing these models into React. I select the meshes, go to File, choose Export, select the format, specify the file name and location, and enable Selected Objects Only. After that, I place the exported file into the public folder. To load the model, I use a dedicated hook. And to render a specific node, I use the primitive tag. A node can represent either a single mesh or a group of meshes. As you can see, the mesh on the right is rendered incorrectly. The issue is caused by inverted normals. One option would be to use a double-sided material, but in this case, I'll add additional geometry instead, so the model renders correctly from the inside as well. Next, for this geometry, I created a new black material and slightly adjusted the metallic value. This immediately makes the inside look much better. I also want to show how I created the additional components: the battery, the chip, and the vibration motor. Using the built-in menus, I can create different types of geometry and modify them. I started with a cube and adjusted its dimensions to match the size of the watch. Then I slightly rounded the edges and enabled auto smoothing. After that, I assigned the black material I had already created. Next, I selected the geometry where a texture was needed and created a new material for it. Instead of using a solid color, I assigned a texture and loaded an image. The texture is stretched incorrectly at first, but I can control its behavior in the UV tab. I rotate it and scale it to properly fit the surface. I use the same approach for the chip and the vibration motor. To finish the preparation process, I want to show how the display texture is set up. Even when the lights are turned off, the texture remains visible, just like a real screen. This is achieved using emissive lighting. The image is not connected to the color channel, but to the emissive channel instead. After some minor refinements, we end up with the following scene. Here, I duplicated 2 additional displays and placed them on the sides, and also added some text and decorative elements. The textures were created in advance using Canva, but you can use any image editing tool you prefer. Next, I exported the watch model into React and rendered the entire scene. This is how the model looks inside the interactive engine. Let's adjust the lighting a bit. By the way, Three.js provides many different types of lights that you can experiment with. They can make your scenes more dynamic and visually appealing. However, we'll stick to the basic examples for now to keep things simple. Let's briefly step away from 3D graphics and focus on implementing the animation mechanism. To do that, I'll move the scene code into a separate file and temporarily comment it out. Instead, I'll create a standalone component where I can test the animation logic in isolation. Inside this component, I add a simple block, set its position to fixed, and center it on the screen. I also add an event listener that handles scroll events on the document. Inside the handler, I log the scroll delta along the y-axis to the console. Now, when I scroll the page, I can see the vertical mouse wheel values in the console, and I can use them as input for the animation. This raises an important question. How can we use scroll input to create 4 sequential states, where the initial cube smoothly transitions between different positions? To store the key positions, I define an array of objects. Each object represents a key state with its own value. I also introduce 2 variables. The first one stores the index of the current screen, and the second one stores the current progress value. During scrolling, I update the progress value. To slow the motion down, I multiply the scroll delta by a small factor, 0.05. When the progress reaches 100, I move to the next state. If the scroll delta is negative, the progress decreases, and once it drops below 0, I switch back to the previous screen. To calculate the current position, I use a separate helper function. This function takes the current keyframe, the next keyframe, and the progress value. The core line of this function returns an interpolated value between the 2 keyframes, based on the current progress. For example, if the current value is 50 and the next value is 75, when progress is 0, the result is 50. When progress is 4, the result becomes 51, and this continues smoothly up to 100. This is how the animation works in practice. At the very end, the block disappears and we see an error in the console. This happens because the code tries to access an element at index 3 plus 1, while the array only contains 4 elements. I installed a state manager and moved all the animation logic into the store. While doing that, I slightly modified the logic, but the core idea remained unchanged. For each state, I added a name that I'll later use to control the interface. I defined index and progress variables and created getters to access the current state, the next state, and the block position. Below that, I defined a function that updates the progress value based on scroll input. At the beginning of this function, I added logic to clamp the first and last states to avoid errors. I also implemented the state transition logic there. At the bottom, there's a function responsible for initializing the scroll listener. It's important to note that this animation mechanism is event-based. In this case, it's driven by scroll events. You can combine this approach with frame-based animations to make the motion smoother. However, that would increase the complexity of both the logic and the code. Since my goal here is to demonstrate the fundamentals, I'm keeping things simple. You can switch to frame-based animations at any time by updating the logic inside the store file. I access the store through a dedicated variable to make the code easier to read and navigate. In the main file, I initialize the scroll listener. In the test file, only the rendering logic remains. At this point, everything works correctly, without errors, and the code is much cleaner. I'll use the same animation mechanism to move the watch model later on. However, instead of moving the model itself, I move a wrapper block. This is important because, in the second state, the camera rotates around a pivot point located on the right side of the screen. If I simply move the model while keeping the camera focused on it, the model would still remain centered in the viewport. To achieve the desired behavior, I slightly adjusted the offset values and added a wrapper block in the main file, where I dynamically apply the current offset. I also added a visible border to this block to make the animation easier to observe. This is the result I get. In addition, I disabled zooming in the orbit controls. Otherwise, it would introduce unwanted behavior. At this stage, the positioning works correctly. However, in the final version, I also changed the camera's field of view during transitions between states. This functionality already works out of the box when I manually update the camera position for each state. What I need now is to drive these changes automatically based on the current scroll index. To do that, I added a field of view value to each state. Finally, I moved the camera control logic into a separate component. In 3D engines, rotations are not defined in degrees, but in radians. That's because all trigonometric functions operate using radians. In this measurement system, 360 degrees equal 2 pi. Using a helper function, I can calculate the angle at which the camera is positioned relative to the center of the scene. The initial value is 1 pi, which corresponds to 180 degrees. In the configuration file, I store angle values in degrees relative to the initial position. In the first state, the offset is 0 degrees. In the second state, it's minus 45. In the third state, it's plus 45. And in the last state, it goes back to 0. In the code, I dynamically compute the camera angles in radians for each state, based on the initial angle. To do that, I convert degrees to radians and add the base angle. As a result, I get the camera angles for the current and the next state. In fact, if I temporarily comment out the state-based logic and replace useEffect with useFrame, I can log camera values every few seconds. And if I manually rotate the camera for the second state, I'll get roughly the same value that was previously logged to the console. Now I can remove the green border that I used earlier for testing. UseFrame is essentially the equivalent of requestAnimationFrame in JavaScript. It runs on every frame, roughly 60 times per second. What I actually want to do here is take the current progress value and interpolate the camera angles in radians, in the same way I did earlier with the block position. However, Regular linear interpolation doesn't work well for angles because angles are cyclical. That's why I implemented a separate function that interpolates angles along the shortest path. You can dive into the math behind it on your own if you're interested. Once I have the interpolated angle, that alone is still not enough. I can't simply assign this value directly to the camera. The camera is always focused on the center of the scene. If I only change the rotation angle at the current position, the focus point will shift in an unintended way. Instead, I update both the camera position and the angle, and then explicitly tell the camera to look at the center of the scene. This way, I achieve the correct viewing angle. This is what the implementation looks like in code, and this is the result in practice. When I try to manually change the orbit control rotation, I get incorrect behavior. This happens because I'm modifying the vertical axis, which breaks the intended logic. To fix this, I simply lock the vertical rotation. Now the dynamic angle interpolation works correctly, even when I attempt to rotate the camera vertically. During the second screen, the watch itself should stay static, while the internal components should move instead. Because of that, I add a new state where both the camera angle and position are identical to the previous state. While on the second screen, I exit the camera interpolation logic because it interferes with the orbit controls. This allows me to freely rotate the camera during that state. However, this introduces a problem. The system always interpolates between fixed, predefined states. But during the second screen, I allow the camera angle to change dynamically. The animation logic is not aware of this dynamic change, so when I scroll to the next state, the camera suddenly snaps back to the base angle before continuing the animation. To better illustrate this issue, I prepared a simple visualization. When transitioning from the first to the second state, the camera moves as expected. If I don't use orbit controls on the second screen, the transition to the next state is smooth and behaves correctly. But as soon as I rotate the camera on the second screen, the next transition causes a sharp jump back to the predefined base angle, and only after that does the animation continue. The same issue occurs when scrolling back in the opposite direction. To fix this, I implemented dynamic angle tracking during the second screen. I introduced a value that stores the current camera angle, along with a function that updates it. Inside useFrame, I update this value on every frame while I'm on the second screen. If a dynamic angle exists, I use it as the interpolation source. When scrolling backward, I apply it as the next angle, and when scrolling forward, I apply it as the current angle. I also added a small fix inside the progress update function to reset the dynamic angle when leaving this state. As a result, the transition now remains smooth, even when I rotate the camera manually on the second screen. Finally, I limit the minimum and maximum horizontal rotation angles, so the user doesn't have too much freedom and the camera stays within controlled bounds. The next step is to implement animations for the internal elements. For a moment, I go back to Blender to better understand the task. As you might remember, this is exactly the screen where I split the model into multiple meshes. If I select any mesh, I can change its position in space using the transform tools or by using keyboard shortcuts. I define positions for the elements that represent a keyframe where they are maximally offset from their base position. Now, back in React, I want to implement interpolation for each of these elements during the second state. Based on the progress value, I change their positions in such a way that at 50% of the progress, they reach their maximum offset, and then reverse direction and move back. In this setup, I render the entire scene as a single object. If I log the scene to the console, I can see that it contains 10 child elements. This structure comes directly from Blender, and each of these elements has its own unique name. To add animation logic, I create a separate component that is responsible for handling the watch model. Inside it, I define an object that describes animation values for each element. This includes the base position and the offset position, which I copied directly from Blender. On every frame, I compute a normalized progress value that goes from 0 to 1, and then back to 0. Based on this value, I calculate the offset for each element by interpolating between the base and offset positions. As a result, I get the following animation. Next, I also want to add a hover effect, where the material of the active mesh changes when the user moves the cursor over it. I go back to Blender again to better understand how this should work. If I select the display mesh, I can see a list of materials assigned to it. When the user hovers over an object, I want to remove all existing materials and apply a custom highlight material to the entire mesh. When the cursor leaves the object, the original materials should be restored. Right now, I'm rendering the entire scene as a single object, but nothing prevents me from rendering each part of the model separately. As an example, I'll render only the display. I already have a list of all child elements, so I can render each node individually. To render a node, I created a separate component where I implemented cursor hover logic. At this stage, these are simple placeholder functions that only log messages to the console. I attach these handlers to a separate group node, because on primitives, they work only with individual meshes. Now, when I hover over the display, I can see the corresponding hover events logged in the console. There is one small nuance here. After hovering over an object, the ray used for object detection continues to propagate. This can result in multiple elements being registered at the same time. To prevent this, I manually exit the handler after the first object is registered. Next, on hover, I want to replace the material of the object with a different one. When the cursor leaves the object, the original materials should be restored. Since different elements may use different materials, I need to store the original material for each mesh in a separate variable. It's important to note that I need to store the material for every mesh inside the groups that make up the base model. If I take the display as an example, I can see that this group uses two materials. When I expand the display in the scene hierarchy, I'll notice that two materials were originally assigned to a single mesh. However, when exporting to the GLTF format, the mesh is automatically split by materials. As a result, the display becomes a group containing two separate meshes, each with its own material. One of these meshes receives an additional name suffix during export, so the engine can distinguish them. To store the material for each mesh, I traverse all child elements within the group. If the element is a mesh, I store its base material. I also created a separate function that updates the material for all meshes inside a group at once. I trigger this function on hover events. When the object is hovered, I apply a custom highlight material. When the cursor leaves the object, I restore the original materials. This is how it works in practice. For some groups, I don't want to apply a hover effect at all, so the logic needs a small adjustment. I moved the element configuration into a separate file to make it easier to manage. For each element, I added a flag that defines whether hover effects are enabled. Before starting the hover logic, I check this value. If hover is disabled, I simply exit the function. As a result, the material swap logic now runs only for elements where hover interaction is explicitly enabled in the configuration. I need to enable the hover effect only on the second screen, so I add an additional condition. At this point, a small bug appears. If I hover over an element first and then continue scrolling, the hover exit event is never triggered. As a quick fix, I add a useEffect hook. When I leave the second screen, I manually reset the material right away. In the final version, I use a custom shader instead of a standard material. I won't go into shader creation here because that topic would take too much time. Let me know in the comments if you'd like a separate video about shader development or other 3D websites I've built. This shader replaces the standard material that is applied during the hover effect. Now the hover effect looks much better. Next, I add the interface for this screen. I create a separate component and implement a state that controls its visibility. When I switch to the second screen, I set it to visible. In all other cases, it remains hidden. I apply basic styles to the container and its child elements. As a result, I get a product description block with a subtle interface animation. In the final version, the description changes when the user hovers over an active element. To achieve this, I add a new configuration value for each child element. This value is an object that contains a name, an icon, and a description. The first element is not interactive, but I use it as the default state. All other interactive elements have their own name and icon defined. I also add a new field to the store to track which element is currently active and display its data. When the cursor enters an element, I store its name in this variable. Inside the interface component, I add a useEffect hook that reacts to changes in the active element. The function hides the content block first and determines which data should be displayed. If an active element exists, I show its data. Otherwise, I fall back to the default information. After that, I display the block again. As the next step, I add the site header. I create a separate component and place it in the main file. Inside it, I add the interface and trigger a fade-in animation a few milliseconds after startup. As you may have noticed, the interface renders slightly faster than the 3D model. In this case, the difference is only a few milliseconds because the model is loaded locally. However, on a remote server, this process can take several seconds, especially on the first visit when there is no cache. To handle this, I add a dedicated state that tracks whether the model has finished loading. Only after the model is loaded do I render the interface. Otherwise, I display a loader. Suspense is used to make React wait for asynchronous resources to finish loading. I pass a callback into the scene component that fires once all resources are loaded. Inside the canvas, I use a dedicated hook that tracks the loading state of the scene. As soon as the scene is fully loaded, I trigger the callback. After all these steps, this is the final result. As the next step, I add an initial animation for the watch model. To do that, I wrap all elements into a separate group and set an initial rotation for it. Then, I create a dedicated ref for this group so I can animate it. In this case, I use the GSAP library to create a smooth transition. Besides the watch model itself, there are several additional objects visible on the first screen. I prepared these models in Blender beforehand. After exporting them, I added a component where I load the model and render each node separately. As a result, I get the following setup. I also added start animations for these elements using GSAP. After the first screen, these elements need to be hidden. To achieve this, I animate their position dynamically along the y-axis. At this point, the first and second screens are complete and look solid. The next step is to add the interface for the color selection screen. I start with the text. For this, I create a separate component that renders the text content. This text should only be visible on the third and fourth screens, so I add the corresponding condition. To make the text feel more interactive, I create multiple copies with different opacity values and reveal a varying number of characters based on the current progress. At the beginning, the text appears too quickly and feels a bit abrupt. To fix this, I add an additional animation for its appearance and a separate condition so it shows up slightly later. In addition to that, I add a separate animation for the transition into the next screen. Next, I create a dedicated component for the color selection interface and implement its internal animation logic. I'll come back to theme and color changes for the model a bit later. When transitioning to the final screen, the site header should also disappear with a subtle animation. To handle this, I add dedicated logic inside the navbar component. For the order screen, I create a separate component. Inside it, I place 4 interface elements: the model name, a button, and 2 screen blocks positioned on the sides. This is how it looks on the page. Then, I add animations for each of these elements based on the progress value. These are all the animations that needed to be implemented. Now we can take a look at the final result. Finally, I need to implement theme switching. During this process, both the material colors and the interface elements change their appearance. I added a separate store where I defined the theme configuration. Each theme is an object that describes 2 values: the material color and the interface color. I need a separate color for the interface because lighting affects material colors in the scene. As a result, the rendered material color doesn't exactly match the original tone. In practice, I usually take a screenshot of the scene and sample an average color to use for the interface. Inside the store, I implemented a getter that returns the active theme, along with 2 functions responsible for switching between themes. In the color selector component, I added a new value that computes the previous and next themes. I connected the store methods to the buttons, and for the active element, I added a separate class to slightly scale the block. Now I need the elements to react to theme changes. I start with the simpler part, the buttons in the site header. Here, I simply apply the active theme color to the background property. Handling the model is a bit more complex. To demonstrate how this should work, I take any material color and go back to Blender. For some materials, I want to override their color based on the active theme. In Blender, this is straightforward. I select the material and change its color through the menu. This is how it translates into code. First, I collect all materials, and then, when the theme changes, I update the color for the predefined ones. The display requires separate logic, since it's implemented using a texture. I added an extra field to each theme where I store the corresponding display texture. Later, I load this texture and assign it to the emissive channel, exactly like I did in Blender. At this point, I notice some inconsistencies, such as the texture being flipped and slight color mismatches. To fix this, I added additional code that corrects these issues. This works well for the current screen, but I also need to update the textures on the first screen. To handle that, I converted the texture variable into an array, and now store 3 textures instead of 1. Inside the component responsible for the 3D props, I added logic that updates these textures dynamically. In addition, I need to update the shader so it reacts to theme changes. The shader is already designed to accept a color through parameters, so I only need to slightly adjust the logic to pass the correct color into the material update function. Now the hover effects work correctly when switching themes, but I still need to update the icon color in the description panel. I also need to apply theme switching on the final screen, starting with the button. Finally, I implement image switching. For this, I added a new field to the theme configuration where I store images for the order screen. Inside the component, I render these images dynamically based on the active theme. As a finishing touch, I added hover effects to some of the interface elements. Now you can take a look at the final result. Thanks for watching, and see you in the next video.